What if NASA found conclusive proof of alien technology, but decided to hide it from the world? 3 weeks ago, a hacker group calling itself Event Horizon claims to have done the impossible, pulling 24 gigabytes of classified mission data from NASA's secure servers. The target? A mission to intercept 3I Atlas, the third interstellar visitor ever detected. The files hint at a cover-up of cosmic proportions. So what did they find that was so disturbing? Let's explore this together. Event Horizon's cyber attack. So how does a clandestine group get its hands on NASA's crown jewels? According to the leaked security logs, this wasn't a brute force attack, it was surgical. In the early hours of September 2, 2025, Event Horizon executed a coordinated cyber attack that bypassed multiple layers of agency firewalls. They exploited a zero-day vulnerability in an outdated Fortran-based mission planning module, a tiny crack in an otherwise formidable digital fortress. The transfer rate was a blistering 571 megabits per second, far too fast for automated security flags to catch in time. Forensic analysts later pieced together a chilling timeline. The attackers gained initial access at 3:14 a.m. Eastern, escalated their privileges to the highest level by 3:19, and began siphoning data at 3:23. In under 7 minutes, 24 gigabytes of compressed files, including internal chat logs, draft reports, and sensitive telemetry from the 3I Atlas intercept mission, were gone. By 3:30 a.m., the connection vanished, leaving behind nothing but a silent gap in the audit trail. Cybersecurity expert Mikko Hipponen has stated that such an attack would require nation-state-level resources, suggesting Event Horizon is far more sophisticated than a typical hacktivist group. The manifesto and distribution. A successful hack is one thing, but what you do next is everything. Hours after the breach, a manifesto from Event Horizon appeared on encrypted forums accessible only through the Tor network. They claimed full responsibility, framing the attack not as an act of digital vandalism, but as a necessary response to what they termed unlawful cosmic secrecy. Their message was a direct challenge to the global intelligence status quo, echoing the methods of groups like WikiLeaks but with a far more specific target. They warned that the leaked files contained material so sensitive that even senior directors at NASA were allegedly kept out of the loop. Their language was blunt: the world deserves to know what its own scientists have found. But Event Horizon didn't just dump the data online. Instead, they began a calculated campaign, distributing blurred screenshots and heavily redacted memos to select journalists and online channels known for covering classified science. No one received the full archive. It was a strategic drip feed, designed to build pressure and credibility, giving the world just enough of a glimpse to understand the immense gravity of what had been taken. Their final warning was a gauntlet thrown down. The files contain evidence that will force the public to confront a new reality. Authenticating the documents. In the world of leaks, authenticity is paramount, so are these files real? The evidence presented by Event Horizon is compellingly layered. The leaked screenshots are plastered with authentic details: bold, block-lettered confidential stamps, thick redaction blocks, and metadata tags showing UTC timestamps that perfectly match the breach window from NASA's own security audit. We see mission patch artwork in the corners, a stylized comet labeled 3I Atlas int. Every document carries unique identifiers, routing codes, and internal chat handles you'd expect to see inside a major agency. Technical diagrams and draft tables use Courier font headers and bear NASA's internal digital watermark. We even see screenshots of the classic blue and white NASA email interface, with subject lines like Atlas intercept, immediate action required, and telemetry review, anomaly detected. One partially blurred memo lists technical trajectory data, while another redacted report is marked with the access level TSSCI, denoting top secret, sensitive, compartmented information, a classification that restricts access to a small, specific group of cleared individuals. The documents bear digital signature strings ending in JPL for the Jet Propulsion Laboratory, and GSFC for the Goddard Space Flight Center, indicating a multi-center collaboration. Discovery of 3I Atlas. Before the leak, there was the discovery. On July 1, 2025, the real-life Atlas survey in Hawaii, a NASA-funded planetary defense system officially known as the Asteroid Terrestrial Impact Last Alert System, logged a new object tearing through the solar system at an astonishing 130,000 miles per hour. or about 58 kilometers per second. Astronomers immediately flagged it. This was the third interstellar object ever detected, following the bizarre one I/Oumuamua in 2017 and the more conventional 2 I/Borisov in 2019. But 3I Atlas was different. Early estimates put its size at a staggering 26 kilometers across, roughly the size of the asteroid Vesta, and over 25 times longer than Oumuamua. Its trajectory, calculated by the Minor Planet Center, confirmed it was an interstellar visitor on a one-way ticket through our system, with an orbital eccentricity greater than 6.0. Its path was hyperbolic, meaning it wasn't captured by our sun's gravity and would not be coming back. According to Dr. Larry Deneau, the principal investigator for the Atlas project, an object of this size and velocity is a once-in-a-century detection event. This wasn't just another icy rock, it was an unprecedented anomaly from deep space. Impossible physics and trajectory. Here's where the story takes a sharp turn from unusual to unbelievable. Like its predecessor Oumuamua, 3I Atlas was not behaving according to the laws of physics. The leaked mission logs from July 18, 2025, show a sudden, inexplicable sideways acceleration resulting in a velocity change or delta V of 1.5 meters per second. The object changed course in a way that defied gravitational models. For a normal comet, such a deviation could be explained by outgassing, measured by the non-gravitational acceleration parameter A2. However, just like with Oumuamua, initial observations of 3I Atlas showed no cometary tail, no dust, and no gas coma to account for the push. Its A2 parameter was effectively zero, yet it was still maneuvering. Trajectory analysts were stumped. They ran models accounting for solar radiation pressure, gravitational pulls from planets, and every known natural force. Nothing matched the telemetry. Dr. Amy Mainzer, a leading expert on asteroids, has noted that explaining such a deviation without observable outgassing requires, quote, exotic physics or an artificial origin. The numbers kept pointing to a single, unsettling conclusion. Some force other than gravity was steering this massive object through our solar system. Surface anomalies, the armor problem. When the first high-resolution images from the Intercept mission were allegedly taken, the mystery of 3I Atlas deepened. The object's surface looked nothing like any known comet or asteroid. Analysts flagged a disturbing pattern. Bands of smooth, almost metallic-looking plating, broken by lines that ran too straight and were too evenly spaced to be natural fractures. These weren't the chaotic, jagged fissures seen on Comet 67P by the Rosetta mission. They were seams, crisscrossing the surface in a deliberate grid. One analyst, in a leaked internal chat, dubbed it the radiator problem, referring to a network of raised ridges spaced like the cooling fins on a spacecraft. These ribs cast long, uniform shadows, and their regularity was so pronounced that pattern recognition software reportedly flagged them as artificial. The object's albedo, or reflectivity, was measured at 0.7, closer to polished metal than the asphalt dark surface of most comets, which have an albedo below 0.05. Planetary geologist Dr. Carolyn Porco has emphasized that nature does not produce such perfect, large-scale geometric patterns. This wasn't just an odd rock, the leaked images suggested it might be wearing armor. Thermal signatures and heat pulses. If the surface looked engineered, the thermal data was even more alarming. According to the leaked files, infrared arrays recorded heat vents pulsing with incredible regularity. The logs show heat pooling along the strange, ribbed seams and then bursting outward in tight, directed jets. This wasn't the broad, chaotic outgassing you see in a typical comet. These were discrete, timed pulses occurring precisely every 90 seconds, raising local surface temperatures by over 200 degrees Kelvin in an instant. The mission logs classified this as a directive motion event, a term typically reserved for spacecraft thrusters, not natural phenomena. Even more damning, trajectory analysts correlated these thermal pulses directly with the object's mysterious course corrections. After each 90-second heat burst, the Intercept team logged a subtle but precise shift in its path. The efficiency of this propulsion, measured as specific impulse, was calculated to be far beyond any chemical rocket, consistent with advanced ion or plasma thrusters. Gravity couldn't explain it, solar radiation is constant, and natural outgassing is random. The evidence was building 3I Atlas wasn't just moving strangely, it appeared to be actively propelling itself. Chemical composition mysteries. The story gets even stranger when you look at the chemical makeup. According to a leaked memo from the Goddard Space Flight Center, the first full infrared spectrum analysis of 3I Atlas yielded a bizarre result. The spectra lit up with incredibly sharp lines of nickel. Now, nickel itself isn't entirely unusual in space rocks. It's often found in iron-nickel alloys. But here's the kicker. In the data for 3I Atlas, the signature for iron was almost completely absent. In the entire catalog of known asteroids and comets, a composition of refined nickel without its constant companion, iron, is unheard of. Furthermore, the memo noted the absence of common silicates and carbonaceous compounds. Meteoritics expert Dr. Meenakshi Wadhwa has confirmed that such a separation of nickel from iron requires industrial-scale processing at very high temperatures, a process not known to occur in nature. It suggests a material that has been engineered, not one that formed naturally. The memo was allegedly sealed within hours under a restricted access embargo, but the data was clear. An object with an artificial structure was made of an equally artificial material. Radio echoes and communication patterns. Beyond its motion and materials, the most chilling evidence in the leaked files points toward active technology. According to the logs, radio astronomers reviewing raw data from the Intercept mission flagged a pattern of faint, repeating echoes in the X-band frequency range. These weren't natural radio bursts or cosmic static, they were precise, clipped signals with a high signal-to-noise ratio, bouncing back from 3I Atlas at regular intervals. What made this truly shocking was the timing. The interval of the radio echoes mapped almost perfectly to the 90-second rhythm of the object's thermal pulses. It was as if something was pinging the object, and the heat pulses were the response. In one of the leaked chat logs, a veteran telemetry specialist reportedly wrote, "It's like someone is pinging the probe and it's answering. The pattern is too tight for random noise." This completely changed the nature of the investigation. SETI pioneer Dr. Jill Tarter has long argued that a truly intelligent signal would likely be efficient and information-dense, characteristics that align with these alleged repeating echoes. The data suggested it could be an active, responsive probe. Expert analysis and propulsion theory. This is where a very real and very famous scientist enters the picture, Harvard astrophysicist Avi Loeb. While he has not commented on this alleged leak, his previous analysis of Oumuamua via the Galileo project provides a stunning framework. The leaked analysis of 3I Atlas goes even further than Loeb's theories. The directed heat pulses and course corrections are consistent with a sophisticated ion drive or a similar propulsion system. But the alleged smoking gun came from a microscopic fragment recovered by the interceptor's dust collector. Under an electron microscope, technicians reportedly saw a lattice of silicon with doped traces of phosphorus, arranged in layers spaced at micron intervals, identical to the architecture of a semiconductor wafer, with visible PN junctions. A materials scientist would immediately recognize this structure. No known natural process from supernova shockwaves to planetary formation can create such ordered, layered microstructures. The memo's summary line, though partially redacted, was legible. Semiconductor structure detected. Artificial origin cannot be excluded. This single finding, if true, moves the conversation from anomaly to artifact. So, what do we make of all this? A 26-kilometer object from another star system moving at impossible speeds, making its own course corrections. It has a surface that looks like armor, a composition of refined nickel, and it pulses with heat and radio echoes on a perfect 90-second clock. And finally, there's a fragment of what appears to be a microchip. The leaked files, if authentic, present a disturbing and profound reality. The questions are staggering. What is this object's purpose? Where did it come from? And perhaps most importantly, what else has NASA found that we don't know about? Don't forget to like, subscribe, and hit the bell icon for more deep dives into the secrets of science and technology. Thanks for watching Sci and Why. An object from another star system is blazing through our own, and it's putting on a show that has astronomers scrambling. This isn't just another rock, it's an interstellar messenger that's rewriting the rules as it gets closer to our sun, glowing 6 times brighter than anyone predicted. What is fueling this incredible outburst, and what secrets from a distant star does it carry? Let's explore this together. The numbers don't lie. So what do we actually know about this visitor? Let's break down the hard data. Right now, the interstellar comet designated 3I Atlas is roughly 2 astronomical units from the Sun. That's double the distance between the Earth and our star, about 300 million kilometers. Its speed is almost difficult to comprehend. It's currently traveling at nearly 60 kilometers per second and is still accelerating. By the time it makes its closest approach to the Sun, that velocity will peak near 68 kilometers per second. To put that in perspective, that's more than twice the speed of any planet, and fast enough to travel from the Earth to the Moon in a little over an hour. On the brightness scale, 3I Atlas has reached an apparent magnitude of 12. While that's about 250 times too faint for the naked eye, its brightness has been climbing far more rapidly than any models predicted. Its coma, the cloud of gas and dust surrounding the nucleus, has expanded explosively, now rivaling the diameter of Jupiter. While a typical comet nucleus is only a few kilometers across, this expanding atmosphere is what makes it so visible. The sheer scale of this coma is a key reason why it's appearing so much brighter than expected. The unexpected brightness surge. Why is this object causing such a stir? It all comes down to a sudden dramatic change. In September, 3I Atlas experienced a massive surge in brightness that defied all expectations. The light curve, which is the chart astronomers use to track an object's brightness over time, shot sharply upwards, veering completely off the predicted path. This wasn't a minor increase. The object is now glowing 6 times brighter than models had forecast, a jump of nearly 2 full magnitudes. This jolt sent a wave of excitement and debate through the astronomy community, with experts like Matthew Knight, a specialist in cometary outbursts, analyzing the data. The core of this mystery lies in its coma, the vast cloud of gas and dust that surrounds its nucleus. As the comet gets closer to the Sun, its ices are vaporizing at an accelerated rate, causing the coma to swell to an enormous size, now spanning several 100,000 kilometers. This giant cloud is reflecting and scattering more sunlight back towards us, making the entire object appear far brighter in our telescopes. The rapid brightening suggests that highly volatile ices like frozen carbon monoxide or carbon dioxide, which vaporize farther from the Sun than water ice, are driving the activity. Racing against the Sun's glare. For astronomers on Earth, the clock is ticking. By early October, the window to observe 3I Atlas is closing, and fast. Every evening the comet appears lower in the twilight sky, getting progressively closer to the blinding glare of the Sun. The angle between the comet and the Sun, what astronomers call solar elongation, will shrink below 30 degrees by October 21st. That's the critical threshold where even the world's most powerful ground-based telescopes, like the Very Large Telescope in Chile, can no longer distinguish the comet's faint glow from the overwhelming brightness of the sky. Amateur astronomy networks are in a frenzy, trying to capture the last possible images before the blackout. Professional observatories, bound by strict safety protocols to protect their sensitive equipment, have already begun to scale back their observations. Pointing a multi-million-dollar telescope too close to the Sun is a risk few are willing to take, as it can permanently damage the sensitive optics. This data blackout is happening just as the comet is expected to reach its most active and interesting phase, leaving a huge gap in our understanding. Mars, the last outpost. Just as Earth's view is about to be lost, the observational challenge shifts 225 million kilometers away to Mars. For a short but critical window, the red planet becomes the only outpost with a front-row seat. A fleet of robotic orbiters will become our eyes and ears. The European Space Agency's Mars Express can capture high-resolution images and chemical fingerprints of the coma. The ExoMars Trace Gas Orbiter is designed to sniff out faint traces of gases like water and carbon dioxide, giving us clues to its composition. NASA's MAVEN, led by principal investigator Bruce Jakosky, can use its ultraviolet spectrograph to study emissions from the comet's gas and dust, while the Mars Reconnaissance Orbiter could potentially resolve the nucleus itself with its powerful HiRISE camera, which can see features as small as 1 foot across from an altitude of 300 kilometers. On October 3rd, 3I Atlas will pass within 28 million kilometers of Mars, close enough for detailed study, but far enough to avoid any danger to the spacecraft. This encounter is our last, best chance to gather close-range data before the comet disappears from view. The Green Mystery. One of the most captivating features of 3I Atlas is its stunning green glow. What's causing this otherworldly color? Spectral analysis points directly to a molecule called diatomic carbon, or C2. Here's how it works. As the comet gets pummeled by solar radiation, the sunlight breaks apart larger carbon-rich parent molecules on the surface through a process called photodissociation. This process excites the resulting C2 molecules, and as they relax back to a lower energy state, they release photons of light specifically in the green part of the spectrum, primarily in what are known as the swan bands around 510 nanometers. This phenomenon is seen in many comets, but the intensity of the green hue in 3I Atlas is exceptional. The work of Nobel laureate Gerhard Hertzberg, who pioneered the study of molecular spectroscopy, provides the foundation for understanding these emissions. This color is a real-time indicator of how rapidly the comet's surface is changing and shedding material as it barrels towards the sun. The impossible anti-tail. As if a green glow wasn't strange enough, some observers have reported something even more bizarre, a faint feature pointing towards the sun. This is a so-called anti-tail, and it appears to defy the laws of physics. We normally expect a comet's tail to be pushed away from the sun by solar wind and radiation pressure, a phenomenon seen in famous comets like Comet Arend-Roland. However, the unique geometry of this encounter combined with the comet's incredible speed creates a different phenomenon. As 3I Atlas ejects larger dust grains, those particles are less affected by solar pressure and tend to remain in the comet's orbital plane. From Earth's perspective, as we cross that plane, some of this dust can appear to project towards the sun, creating a sunward spike. The late Michael A. Hearn, a leading expert in cometary dust, developed models to explain these complex dynamics, showing how electromagnetic forces can sometimes rival gravity's influence on charged dust particles. While reports of the anti-tail are still tentative, its presence would add another layer of intrigue to this already mysterious visitor. Not like the others. So, to truly understand just how unusual 3I Atlas is, we have to compare it to the only other interstellar visitors we've ever seen. The first, 1I Oumuamua, discovered back in 2017, was a bizarre, cigar-shaped object with a high orbital eccentricity of 1.20 and, no visible coma or tail at all. It was basically a dry, inert shard just tumbling through our solar system. Then 2 years later, 2I Borisov arrived, and it looked way more like a classic comet, with an even higher eccentricity of 3.3. It had a bright coma, a well-defined dust tail, and a chemical makeup that was pretty similar to comets from our own Oort cloud. But 3I Atlas just refuses to fit into either of these boxes. Its coma is not only massive but also intensely green, which is a sign of strong diatomic carbon emission, something we just haven't seen with this kind of intensity in Borisov. And its dramatic brightness surge, a 6-fold increase above predictions, is unlike anything we've seen with the other two. According to University of Hawaii astronomer Karen Meach, this diversity really shows we have much to learn about the small body populations of other star systems. The Mars Encounter Strategy. The hopes of the entire astronomical community now rest on a handful of spacecraft orbiting Mars. Mission planners have spent weeks preparing for the October 3rd flyby, running simulations and allocating precious observation time. The goal is to get a multifaceted snapshot of the comet that would be impossible from Earth. Scientists want to use the high-resolution cameras like MRO's HiRISE, which has a 0.5-meter primary mirror, to try and spot the nucleus and measure its size and shape. Spectrometers will analyze the light from the coma to map the chemical composition of its gas and dust, telling us what kind of alien ices are vaporizing off its surface. Plasma instruments will study the interaction between the comet's atmosphere and the solar wind. No single spacecraft can do it all, and none have promised continuous coverage, but by combining data transmitted through the Deep Space Network, scientists hope to piece together a comprehensive profile of this interstellar visitor. It's a difficult observation, but the potential payoff is a groundbreaking understanding of a body from another star system. Chemistry in motion. Let's dive deeper into the chemistry that makes 3I Atlas so fascinating. The dominant green glow comes from diatomic carbon C2, but it's not the only molecule at play. Some early spectral readings have hinted at the presence of ionized carbon monoxide and the cyanogen radical, both of which can also contribute to a green or blue glow. Debates have already started in scientific forums about the precise mix of these chemicals. often relying on data from powerful spectrographs like the X-shooter instrument on the VLT, which can cover wavelengths from the ultraviolet to the near-infrared in a single shot. The comet's incredible speed is a key factor here. It means that solar radiation is stripping away fresh, pristine ices from the nucleus at an astonishing rate. We are not just seeing ancient processed material from the surface. We are likely getting a look at the primordial parent molecules that were frozen inside this object when it formed billions of years ago in a completely different planetary system. This makes 3I Atlas a unique chemical laboratory. The fade begins. What happens after 3I Atlas swings around the sun? Its brief moment of glory will be over and the fade will likely begin. Most models predict a sharp drop in brightness as the comet speeds away from the sun's heat, its vibrant coma shrinking and dispersing back into the void. For anyone hoping to catch a final glimpse, it will be a challenge. A large telescope with at least a 20-centimeter mirror will be the absolute minimum, and even then, it will likely appear as just a faint, fuzzy smudge. This is where citizen science will take over. Amateur astronomers and online networks similar to the American Association of Variable Star Observers will pool their observations, using techniques like image stacking to track the comet's retreat. These platforms provide real-time updates on its position and brightness, creating a light curve that professional astronomers will use to understand its behavior. The story doesn't end when it gets dim. Studying the post-perihelion light curve can reveal crucial details about the comet's structural integrity and whether it survived its fiery passage intact. The journey of 3I Atlas through our solar system, though brief, leaves us with more questions than answers. Each data point gathered from this mysterious visitor helps us understand the diversity of objects that wander the galaxy. What does its unique composition tell us about the planetary system where it was born? How many more of these interstellar travelers are out there waiting to be discovered? As it slips back into the darkness, 3I Atlas reminds us that our solar system is not an island, but part of a vast, interconnected cosmos. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thank you for watching Sci and Why. What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, where does a story like this begin? It starts with our ever-watchful eyes on the sky. The story began on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey telescope at the El Sos Observatory in Chile, detected a faint object with an initial apparent magnitude of plus 19.5. To put that in perspective, that's about 250,000 times fainter than what the human eye can see. When astronomers calculated its orbit, they saw something remarkable. Its path was hyperbolic with an orbital eccentricity calculated to be a staggering 1.8. In astronomy, any orbit with an eccentricity greater than 1 is unbound. This number confirmed it was moving at approximately 55 kilometers per second relative to the Sun, far too fast to be a member of our solar system. Astronomers quickly named it 3I Atlas. Initial estimates suggested it could be massive, between a few hundred meters and several kilometers across, making it potentially much larger than the previous 2 interstellar visitors. The discovery was a major success for the ATLAS network, which also includes telescopes in Hawaii and South Africa, proving its effectiveness in spotting these rare cosmic travelers. The detection of a third such object in less than a decade confirmed that these visitors are more common than previously thought, officially opening a new frontier in astronomy. Avi Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArcSiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. You can imagine what happened next. The words alien technology from a prominent Harvard astronomer ignited a media firestorm. The idea was captivating, offering a sensational explanation for a new cosmic puzzle. But this is where the rapid world of headlines collides with the methodical, patient pace of science. The scientific method isn't about finding the most exciting answer, it's about finding the one that best fits all the evidence. The broader astronomical community, while not dismissing Loeb's right to speculate, emphasized the need for patience and adherence to Occam's razor, the principle that the simplest explanation is often the best. Their stance was clear: we must first rule out all known natural phenomena before jumping to an extraordinary conclusion. The use of preprint servers like ArcSiv allows for rapid dissemination of ideas, but also bypasses the traditional peer review process, meaning speculative ideas can reach the public before they are fully vetted by other experts. Ultimately, the scientific consensus held that declaring an object alien required the elimination of every single possible natural explanation first, a very high bar that had not yet been met. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph, NIRSpec, to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events, thanks to its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave, honestly, no stone unturned, to precisely measure its path to within a few milliarc seconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what did this powerful array of telescopes actually see? The answer was unambiguous, and came sooner than many expected. As 3I Atlas drew closer to the Sun, crossing the orbital distance of Jupiter at approximately 5.2 astronomical units, which is about 483 million miles, the solar radiation began to warm its icy surface. Just as predicted by standard cometary models, it started to sublimate, behaving exactly like a comet. Astronomers watched as it developed a distinct coma, the fuzzy, gaseous atmosphere around its nucleus, which grew to over 50,000 kilometers in diameter. Shortly after, a classic tale of gas and dust began to form. Tom Statler summarized the findings. It looks like a comet. It does comet things, and the evidence overwhelmingly points to it being a comet. The observation of outgassing, with a dust production rate estimated at over 50 kilograms per second, provided the natural explanation for any minor deviations in its path, rendering the artificiality hypothesis unnecessary. This behavior began right around the frost line where water ice turns to gas, a telltale sign of a natural cometary body. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope's spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis, revealed familiar substances like water ice and carbon dioxide, but with a major surprise, 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk, where carbon dioxide could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, which is a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With the "what is it" question settled, NASA also moved to definitively address any public concern about its path. The coordinated tracking campaign from both space and ground-based telescopes allowed for an extremely precise calculation of its orbit. The agency confirmed that 3I Atlas posed absolutely no threat to Earth. Its closest approach to our planet will be a very safe 1.8 astronomical units, which is about 273 million kilometers or 170 million miles away. Its perihelion, or closest approach to the Sun, is predicted for January 12, 2026, at a distance of 1.5 AU, placing it between the orbits of Earth and Mars. NASA's Planetary Defense Coordination Office used this as a perfect real-world test of their tracking systems, proving they can accurately predict the path of even novel interstellar objects with incredible precision. After it loops around the Sun, its hyperbolic trajectory will ensure it is flung back out into interstellar space, never to return. Its brief passage is a fleeting but precious scientific opportunity. Natural anomalies in cometary physics. The whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29P Schwarzmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of a million, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4 or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They are part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science, they are the very data points that lead to new discoveries about how objects form and evolve. Thus, the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So if 3I Atlas is not alien technology, why is it so important? Because interstellar comets are windows into other worlds. Each one is a preserved time capsule, carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of carbon dioxide and its trajectory suggest it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our Sun was born. By studying its isotopic ratios like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, a key factor in assessing the potential for life elsewhere. This is more than a curiosity, it is a preserved fragment of another planetary nursery. Future missions, like the ESA's Comet Interceptor, are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to analyzing actual, physical samples. Comparing 3 interstellar objects. To truly appreciate 3I Atlas, you have to place it in context with its predecessors. The first, Oumuamua, discovered in 2017 with an eccentricity of 1.2, was a complete enigma. It was small, rocky-looking, showed no visible coma, yet had a mysterious acceleration. The second, 2I Borisov, found in 2019 with a high eccentricity of 3.37, was almost the opposite. Its nucleus was about a kilometer wide and it behaved like a classic comet, allowing for detailed study. 3. I Atlas, with its eccentricity of 1.8, falls between these extremes. It behaves like a comet, which sets it apart from Oumuamua, but its distinctive chemical ratios make it stand out from a standard comet like Borisov. This growing diversity is forcing astronomers to create a new classification system for interstellar objects. The current rate of discovery suggests that at any given time, there are likely thousands of interstellar objects within our solar system, but most are too small and faint to detect. As our technology improves, we can expect to find many more of these cosmic messengers, each one adding another piece to the vast puzzle of our galaxy. In the end, Comet 3. I Atlas isn't alien technology. It's a natural interstellar comet. A stunningly beautiful and scientifically priceless messenger from another star system, shedding gas and dust as it speeds through our cosmic neighborhood. The real story here isn't science fiction, but the incredible power of science itself to solve mysteries and reveal the universe's secrets. It's a rare glimpse of pristine material from another world, reminding us that the cosmos is far more diverse and fascinating than we can imagine. For more deep dives into the mysteries of our universe, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting. Thank you for watching Sci and Why.